All right, good morning, everyone. Mohit, are you there? And if so, do you have anything to say?
Yeah, good morning, Derek. Please go ahead. I do not have anything.
All right, I will start. Oh, Mohit, I need the screen sharing option.
Done.
Thank you. All right. Based on the comments I got yesterday, I thought it would be good to review what we've done so far briefly, and also talk about what the different variables are and kind of bring things together in terms of the development of seismic theory. So we started out with stress, and I noted stress is a 3x3 tensor that describes the force per unit area on a material. The traction vector is the surface force per unit area on a plane with a given normal. And if I take the three planes that are perpendicular to each other, I can get the stress tensor from the traction vectors. The traction can be calculated using Cauchy's stress theorem. So the traction vector equals the stress tensor times the normalized normal vector to whatever plane of interest that you have. And by normalized, I mean the normal vector has to have a length of 1, so you need to normalize that. And again, we will use the engineering convention that tensional stress is positive. So stress in the earth is going to have negative components. Properties of the stress tensor: it is symmetric, so there are only 6 independent variables. We can rotate it into different coordinate systems. So if we want to have x1, x2, and x3, or x1 prime, x2 prime, and x3 prime, it's a simple matter to rotate it into that new coordinate system. And in particular, there's a coordinate system that has no shear stress, and this gives the principal stresses, which are the eigenvalues of the stress tensor. Finally, the trace of the stress tensor is independent of the coordinate system used. So whether you have x1, x2, and x3, or x1 prime, x2 prime, and x3 prime as your axes, the trace of the stress tensor will be the same in both instances, although the off-diagonal components will vary. The pressure is the mean of the trace of the stress tensor, and the deviatoric stress tensor is the stress tensor minus the pressure. Units of stress in MKS units are newtons per square meter, or pascals. And roughly in the earth, a 33-kilometer increase in depth increases pressure by 1 gigapascal. Now, strain defines the deformation of a material in response to stress, and strain can be defined in terms of a displacement, U. How U varies with X will determine the type of strain or the shape of the deformation. And elasticity determines the amount of strain a given stress will cause. The strain tensor is a 3x3 symmetric tensor. So in addition to the stress tensor, the strain tensor has 6 independent components. So now I want to go through the different variables that we've used. So I've used both tau and sigma to denote the stress tensor, and that is just because different books use both variables. Tau and sigma just mean the same thing here. And Cauchy's stress theorem is the traction vector, so it's got 3 components, equals the stress tensor times the unit normal to the plane. And here's an example. The traction vector would be the stress resolved on this particular plane, and the traction vector doesn't have to be normal or along the plane. It can be in any direction. And then it can be decomposed into a shear stress or shear traction and a normal stress or normal traction. U gives the deformation at a given point, x. U is a vector and x is a vector as well. So for instance, if I have a location x and then I apply stress to it, that point x will deform by a value u, and that will be its new location will be x plus u of x. We can define the 3-dimensional variations in the deformation through the strain tensor. So it's given by E sub ij, and it's a bunch of derivatives of the deformation vector with respect to the position vector. Elasticity is a 4th-order tensor that relates stress to strain. So sigma sub ij equals C sub ij KL times E sub KL. So a 4th-order tensor has 81 components in it. It's 3 to the 4th power because it's a 4th-order tensor, where stress and strain are 2nd-order tensors, so they have 3 to the 2nd components, or 9 components. However, if the elasticity is isotropic, which means that for our given small chunk of matter, no matter what direction the elasticity is the same, then the elasticity tensor can be described in terms of lambda and mu. These are called the Lemay parameters, and it follows this formula: C sub ij KL equals lambda times delta ij delta KL plus mu times delta ik delta JL plus delta IL delta JK. Now delta here is the Kronecker delta function. It's 0 if I doesn't equal j and 1 if I equals j. So as an example, I can calculate C sub 1121. So I is 1, j is 1, k is 2, L is 1. And I can write out the Kronecker deltas. So d sub ij is d sub 11, d sub kl is d sub 21, and so on. And in this case, the 2 components do not equal, so that's equal to 0. Delta sub 1, 2, again, it's going to equal 0. Delta sub 1, 2 again, because it's delta sub jk is going to be 0. So this, in this case, C sub 1121 will just be 0. So you can see that with all these Kronecker deltas, you're going to really simplify the 81 component elasticity tensor. And I further described that due to different symmetries, even if I have a non-isotropic substance, we are not going to have any more than 21 free parameters. So for an isotropic substance, we can rewrite the stress-strain relationship in terms of sigma sub ij equals lambda E sub kk delta sub ij plus 2 mu E sub ij. E sub kk is done using the summation notation. So this has a repeated index. So this is E sub 11 plus E sub 22 plus E sub 33. We sometimes indicate E sub 11 plus E sub 22 plus E sub 33 as theta, and that's called the dilatation. And theta or E sub kk in terms of summation notation are just the trace of the stress tensor. And if I write that in terms of the partial derivatives of u with respect to x, I get the trace of the strain tensor is du1 dx1 plus du2 dx2 plus du3 dx3, which is just the divergence of u. So the dilatation, which is the fractional volumetric change, is just going to be the divergence of u. All right, so we do the elastodynamic equation, and we made a number of assumptions, and I didn't derive this, but I did give you the 5 steps that we needed to get from the elastodynamic equation to a simpler solution. So here is the elastodynamic equation. And to solve it, we do a Helmholtz decomposition. So we divide the deformation field up into the gradient of a scalar potential phi and the curl of a vector potential psi. This breaks up the equation into 2 simpler and separate forms. So one equation that we can solve is this here with scalar potential phi, and that's for p waves. And then the second equation has a vector potential psi, and that's for s waves. So phi is the p wave scalar potential, alpha is the p wave velocity, psi is the s wave vector potential, and beta is the s wave velocity, and then t is time. So we have a formula phi of xt equals ae to the I omega t plus or minus k dot x, which is a solution to this previous equation here. And omega is angular frequency. It's equals 2 pi times the normal frequency. K is the wave number vector, and we'll get to that in a little bit. X indicates position. Again, it's a vector. And T indicates time. And the solution to the S wave equation is similar. The only difference is it has a polarization vector. So it's got a 3-component vector in front of the harmonic wavefront, which is given by the exponential term. The p wave velocity alpha is lambda plus 2 mu over rho, which also equals the square root of k plus 4/3 mu over rho. And the s wave velocity is beta equals square root of mu over rho. So lambda is the first Lemay parameter, mu is the shear modulus, k or kappa is the bulk modulus, and rho is the density. So these are the parameters that affect the propagation of seismic waves in the earth. And in particular, seismologists typically think about the bulk modulus and the shear modulus. And these are both pressure and temperature dependent, as well as slightly compositionally dependent. And so with that in mind, we can take velocity variations and infer temperature variations, for instance, in the earth. Now, we have formulas that solve in terms of the scalar potential phi and the vector potential psi. And then what we need to do to actually get displacement, so to get the actual motion of the earth, is we have to do the opposite of the Helmholtz decomposition. So for p waves, I have to take the gradient of phi, and for s waves, I have to take the curl of psi. All right, so the wave number vector, k, defines the path of the propagating wave through space. The vector has a magnitude that is equal to omega over alpha if we have a p wave, and omega over beta if we have an s wave. We can also define the slowness vector, and the slowness vector in 2 dimensions the x component is p, which is the ray parameter, and eta. P is equal to sine theta over v. Eta is equal to cosine theta over v. And P and eta are just 1 over the apparent horizontal velocity and 1 over the apparent vertical velocity. And these two are also equal to k sub x. So the x component of your wave number vector over omega and k sub z over omega. So the horizontal slowness or ray parameter is 1 over the horizontal apparent velocity, which equals sine theta over v, which also equals k sub x over omega. The vertical slowness, so also the ray parameter is constant for a given ray. So P will be the same no matter what layer your wave is propagating through, whereas eta will vary with the velocity of the layer. And that gives 1 over the vertical apparent velocity, which is cosine theta over v, or k sub z over omega. And we can also say that 1 over v squared equals cosine squared plus sine squared theta, where theta is the angle of incidence of your ray, over v squared, and that equals cosine squared theta over v squared plus sine squared theta over v squared. And this just equals eta squared plus p squared. With that in mind, then we can also solve for eta to get it's the square root of 1 over v squared minus p squared. And I think these are all the relationships that you need, with the exception of R, which I will get to do the formulas that we've discussed so far. So theta is the angle of incidence of the ray, v is the velocity in the layer, c sub x is the horizontal apparent velocity, c sub z is the vertical apparent velocity, and omega equals 2 pi f. And I will say c sub x and c sub z are not are not the x and z components of the actual velocity. So these are actually apparent velocities, and you got to be a little bit careful with them. And then finally, we can define the ratio of the vertical to horizontal wave numbers in terms of R. So R sub alpha or beta is going to be k sub z over k sub x, and k sub z is going to vary depending on whether you are talking about P waves or S waves. All right, any questions on that sort of quick review? All right, I will go on into normal modes. Oops. This is section 2.9 in the Stein and Weiss session book. And I posted a PDF of the Stein and Weiss session book in our OneDrive folder, as well as I've given my write-ups where I go through the details of the derivation for things like surface waves, normal modes, and the elastodynamic equation. So those are also now in the OneDrive folder. So normal modes are basically use the second part of wave mode duality. So elastic displacement can be equivalent described by propagating waves or summation of modes. So here I've shown the different vibrational modes, for instance, on a drum. So normal modes can be used to generate synthetic seismograms, especially long period seismograms, and they are often used for that. And we can use them to get estimates of earth structures difficult to get at in other ways, say, for instance, the density of the outer core. So I want to cover these topics: vibrations on a string, Legendre polynomials and Legendre functions, normal modes in the earth, and then we will get to two types of normal modes, toroidal modes and spheroidal modes. We'll talk about usefulness of normal modes, then attenuation of normal modes, and then splitting of these modes. To motivate our discussion, I want to talk about vibrations on a string. So basically the normal modes on a string. So a string attached to both sides will only vibrate at certain frequencies called eigenfrequencies. So these frequencies are n pi v over L, where n is an integer, and displacement as a function of location will be a function of these eigenfrequencies. So we will have the spatial eigenfunction, U sub n, which is a function of your location and your particular eigenfrequency. So for a string, U sub n x comma omega sub n is going to equal sine of omega sub n x over b. And omega sub n is given up here as n pi v over L. So our spatial eigenfunction for a string is sine n pi x over L, where L is the length of the string, x is the location along the string, and n is an integer. There's also a time term since the waves are changing with time. And that time term is cosine of your eigenfrequency times t. So we can put it all together. We have the displacement in terms of space and time equals our spatial eigenfunction times our time variation. And that is just sine n pi x over L times cosine omega sub n over t. So for the fundamental mode, for instance, n equals 1, u of x of t equals sine of pi x over L times cosine pi v over t of L. Pi vt over L. Any point on a string is then a weighted summation of each of the modes from n equals 1 to infinity. So we have a weight here and then the eigenfunctions. And I'd note that the eigenfunctions form an orthogonal basis, which means if you integrate the product of two different eigenfunctions over the length of the string, the result is 0. And if it's the same value, if m equals n, then I have L over 2. The weighting or amplitude for each eigenfunction is dependent on the source of the waves. So a sub n equals sine of n pi x sub s over L times some function of omega sub n, which describes the source. Here is an example for a source at x is equal to 8, and the excitation function is e to the minus omega tau squared over 4. And that gives us then our amplitude function. And basically what we do is we add up all these eigenfunctions going from n equals 1 to n equals 40. And we can see, as we plucked here at a certain time, we have what looks like two waves that have propagated outwards from the point that we plucked it. And we do have some waves that look like they've propagated faster than the inherent velocity of the string. And those will damp down if I go to more and more eigenmodes. So in this case, we could argue that summing the first 40 nodes is not enough to properly depict the location of the wave on the string. All right. So with that to motivate us, now I want to talk about Legendre polynomials and Legendre functions, because we will need them to define the normal modes on the Earth. So first, I want to consider a function f of t. It can be represented by a series of sine and cosine waves of different frequencies. So we can convert f of t into f of omega, and this relationship is called a Fourier transform. So basically, it rephrases the spatial components of a function in terms of the frequency components of a function. The Fourier transform shows that e to the I minus I omega t, or equivalently sine and cosine waves, can be combined in such a way that almost any arbitrary function of t can be made from these. Put another way, that means that sine and cosine waves, or e to the minus I omega t, are basis functions, which means that we can combine individual members of these basis functions to create any arbitrary waveform. So for a sphere, displacement on the surface can be described in an analogous way in terms of spherical harmonics. We will use something called Legendre polynomials and Legendre functions. And the geometry we will use is the earthquake source will be at the North Pole. And then we will talk about the distance theta that the receiver is from the source. And we will talk about displacements in terms of u sub r, which is the up and down displacement, u sub phi, which is a longitudinal displacement, and u sub theta, which is a latitudinal displacement, assuming that the source is at the North Pole. So it's not true latitude, but it's actually a co-latitude. So it's 0 at the source and 90 at the equator if the source is at the North Pole. All right, so Legendre polynomials are given by P sub L equals 1 over 2 to the L power times L factorial d dxl times x squared minus 1 to the L power, where L designates the angular order of the polynomial. So L is going to be an integer value. Now for a sphere, we are going to replace x by cosine of theta. So these are going to vary with co-latitude from the source. We also want to consider longitudinal dependence. So we need to expand the Legendre polynomials to a more general set of Legendre functions. And so these Legendre functions are P sub L sup m of x, and that is the quantity 1 minus x squared to the m over 2 power times 2 to the L power L factorial times the L plus m derivative with respect to x of x squared minus 1 to the L power. This will turn into the Legendre polynomial when m equals 0. And here the azimuthal order m varies from minus L to plus L. So m cannot be greater than L. So these can be combined with e to the I m phi to form a basis set of spherical harmonics. And there will be different basis sets for the different types of normal modes. So we haven't quite defined the normal modes yet, but we will. First, I want to give an example for how you might calculate P sub Lm for m equals 1 and L equals 1. So here's the formula up in the upper right here. for P sub L sup M. So the first thing we do is we calculate it with respect to X. So P sub 1 sup 1 is going to be this 1 minus x squared to this 1/2 power over 2 times the second derivative, because it's the L plus M derivative. And L is 1 and M is 1, of x squared minus 1 to the 1 power. I take the one derivative of this, that gives me 2x. I take another derivative of this, that gives me 2. And therefore, P sub 1 sup 1 of x is going to be 1 minus x squared to the 1/2 power. The next thing I will do is I will substitute in cosine theta for x. So where there's an x, I'm just going to put a cosine in. So I have P of sub 1 sup 1 cosine theta equals 1 minus cosine squared theta to the 1/2 power. Well, we also know the trig identity that 1 minus cosine squared of theta equals sine squared of theta. And since this is the 1/2 power, it's just sine theta. Now we don't plug in cosine theta initially. We want to do this in terms of x first, and then we plug in the cosine theta. And in the homework, you will have an opportunity to do this. All right, so now we need to expand our spherical harmonics a little bit more. So here I have the Legendre functions times e to the I m phi. And now I want to add in this term here. And this is called y sub L sup m. And these are Laplace spherical harmonics. L designates harmonics that tend to have a dependence on theta, which is a colatitude. And M designates harmonics that contain a phi or longitudinal dependence. So this has 0 in M. So there's no longitudinal dependence, but there is a latitudinal dependence because we have a 2 for the L. This here has a 3 for M and 3 for L. And so we have both a latitudinal and longitudinal dependence. And here we have y of 2 and 4. And this shows you another example. So for normal modes in the Earth, we define it in terms of r. So our vertical displacement, theta, which is our colatitude, and phi, which is our longitude. And we will do a summation over in L and M, where A is the amplitude for each mode, Y is the radial dependent behavior, so the depth dependent behavior, and X is going to be our location dependent behavior. So in terms of our theta and phi, and then we have e to the I sub n omega sub L sup m times t, which gives us our sort of waveform type behavior. So if we know U, so for instance, if we can measure displacement at a location and we know Y and X, which we can calculate, we can learn something about A, which tells us the excitation amplitude. And so that allows us to infer something about the nature of the earthquake that produced the deformation U. Conversely, if I give A, so I prescribe an earthquake, then I can predict U. And then I can actually calculate a synthetic seismogram for any location on the Earth. So there's a program out there called Minios, And actually in my full seismology class, we actually do some practice with it. You can get that from the Computational Infrastructure for Geodynamics webpage, and that will actually calculate normal modes for a given earthquake. So we've noted in the past that PSV.
Sir, sorry, sir.
Yeah.
Could you kindly repeat the website, sir?
Yeah, actually, I'll put it in the chat.
Okay. Okay.
So just Google computational infrastructure for geodynamics, and that should give you access to a number of geodynamic and seismic codes, including MINEOS. And MINEOS is spelled M-I-N-E-O-S. So we've noted in the past that P and SV can be considered one system, and SH can be another system, just like with Rayleigh waves, which are PSV motion, and Love waves, which are SH motion. And we can do the same with normal modes. So PSV motion is described by spheroidal modes. They have horizontal and vertical components to motion. There's no simple relationship between in and nodal spheres, so the locations where there's zero deformation. And S sub 2 and with m equals 0 and n equals 0 is a fundamental mode. So there is not an S of L equals 1. And these affect the whole Earth from the surface to the core. Now, in contrast, toroidal modes have no radial component to motion. So there's no in and out motion with the Earth. The motion is confined to the surface of inconcentric spheres within the Earth. SH or toroidal modes do not have cause the Earth to undergo a volume change. And they also do not exist in a fluid, since fluids cannot have shear. And here's an example of a toroidal mode. So spheroidal, the in component really has no direct relationship with nodes with depth. L gives the nodal planes in latitude, and M gives the nodal planes in longitude. M, like we discussed before, varies between minus L and plus L. We call the L nodes a singlet, and if M is greater than 0, we call it a multiplet. Or if the absolute M value of M is greater than 0, so M can be -1 or +1, then we would have a multiplet. With the toroidal modes, N gives the number of nodal planes with depth, and L, we have L -1 nodal planes in latitude. So for instance, if L equals 3, we have this circle here and this circle here, which gives the nodal planes the planes of 0 deformation. So it's L -1 nodal planes. And then M gives the nodal planes in longitude. And in this case, we'll note that M is equal to 0, so we don't have any longitudinal variation. So what we've done so far is we've said the deformation at any point on the Earth is going to be a sum of N, L, and M of a amplitude function that describes a source times a radial eigenfunction times a surface eigenfunction, which is a vector, times e to the I omega t. We will skip worrying about the radial eigenfunction. It's important, but it's a little too complicated to do for this class. And then we will look at the surface eigenfunction in terms of spherical and torsional modes. And to develop these eigenfunctions, we needed to create a spherical harmonic basis. So we had to create that Y formula. And we started that out with Legendre polynomial. And we calculated that for x equals cosine theta to get longitudinal variations. We expanded this to form the associated Legendre function. And then we expanded that even further to create the fully normalized spherical basis we need. And then the vector spherical harmonics associated with the spherical mode are R sub Lm equals Y sub Lm, comma 0, comma 0. This is the radial component. The 0 is the colatitudinal component, the theta component, and the third 0 is the phi component. And then we also have to consider S sub L sup M, which has 0 radial motion. And then the theta motion is given in terms of this derivative, and the phi motion is given in terms of this derivative. The toroidal motion, the toroidal mode, has 0 radial motion, and then theta motion and phi motion in terms of these two derivatives. So this may seem a little complicated, but really taking this derivative with respect to phi just involves taking this derivative with respect to phi, and this actually will simplify quite dramatically for small values of L or M. So let's look at toroidal or torsional modes, which are SH motion. So our U, our displacement just due to toroidal modes is going to be N and L sum to infinity, and M, which is going to sum from minus L to L. There'll be an amplitude based on the excitation function, the earthquake, the radial eigenfunction, which we are not going to calculate, and then the surface eigenfunction, which is described here. Here are some examples of torsional modes. So this is N equals 0, L equals 2, M equals 0, M equals 1, M equals 2. This is N equals 0, L equals 3, M equals 0, 1, 2, and 3. And this is N equals 1, L equals 2, and M equals 0. You can see even that in this one here that the core is moving back and forth. So basically, when we have a large earthquake, the earth rings like a bell, and we can measure that. In terms of spheroidal or poloidal modes, so PSV-like motion, it's a little more complicated. So we have the amplitude times one radial eigenfunction times a vertical motion, and another radial eigenfunction times theta and phi motion. And the radial eigen or the vertical motion is given by R sub L sup M, and the horizontal motion is given by S sub L sup M. And we can note that the three spherical harmonics are orthogonal. So T of Lm dot S of Lm and T dot R and S dot R are all going to be 0. If, yeah. So here are spheroidal poloidal modes. You can see these involve a little bit more of stretching of the earth, so in and out motion of the earth. So this is L equals 0, L equals 1, L equals 2 for N equals 0, and M equals 0, M equals 1, M equals 2, and M equals 3. So you can see as M increases or L increases, we get a little more complicated modes. So L equals 0, M equals 0 is just a sort of breathing mode. And here's for L equals 1 and M equals 1. This is called the Schlichter mode. And it's useful for inferring the density change at the inner core boundary. So why would we use normal modes? Well, if we can calculate the frequencies of the normal modes, they can tell us something about the shape of the Earth, the bulk modulus, the shear modulus, and density as a function of depth. So what we typically do is we measure the frequency at which a particular mode is excited and use that to infer those several parameters. Normal modes are also useful for simulating phenomena like diffraction that can't be done with ray theory. Eigenfrequencies are sensitive to Earth structure in a way that complements other methods. It's a more efficient way of creating synthetic seismograms that correspond to long time periods, for instance, longer period surface waves. It's not very efficient at calculating high frequency waves like a P wave, but for longer period waves, it is pretty efficient. It's useful for inferring distant earthquake focal mechanisms and also for inferring earthquake magnitude for the largest earthquakes. And I'll show an example of that in a minute. So you may recall there was a tremendous earthquake off the coast of Sumatra. It's called the Sumatra Andaman earthquake. And initially, after recording P waves at 7 stations at 11 minutes after the earthquake, it was calculated to have a magnitude of 8.0. Then after 25 stations were analyzed, the magnitude was revised upward to 8.5. And then surface waves were analyzed at 157 stations, didn't affect the magnitude, but then more stations were analyzed and the magnitude was revised up to 8.9 and then 9.0. And then finally, when they looked at free oscillations, they got a magnitude of 9.3. And free oscillations are just another way of saying normal modes. And then finally, they added GPS displacements and they revised it down a little bit to 9.2. So this shows you, one, that magnitude is for large earthquakes actually takes a complicated procedure to get accurately. And we'll talk about that in a couple of days. But the free oscillations are important in terms of calculating the magnitude of the largest earthquakes. So here is the fault on which the earthquake slipped. Here is the rupture zone is determined using 300 to 500 second surface waves. And then from aftershocks, free oscillations, and GPS, they figured that this whole fault slipped. And they did this by measuring the frequency of different normal modes. So this is S with L equals 2 and N equals 0 at seismometer MAGO. And they calculated the amplitude and the frequency of this normal mode. All right, so modes don't go on forever, which is a good thing because then the Earth would shake apart. So they damp out. And to account for this, we scale our displacements such that each cycle has progressively smaller amplitudes. For instance, for the torsional mode, the scaling is e to the minus omega t times 2q. Q is a value that determines the amount of attenuation. If Q is high, waves will lose their amplitude slowly. If Q is low, then this negative value, this whole exponent, becomes quite large, and things will attenuate or lose their amplitude quite quickly. So for instance, we will modify the torsional mode displacement from this formula to this formula. So we will add this exponential term. Here's an example. So here is a seismogram recorded, and here is the Q factor for two different normal modes. And you can see this one has a slower decay in amplitude, and that means it has a larger Q value. This one has a quicker decay in amplitude, which means it has a lower Q value. And out here, you can see there was another earthquake, which excited some of the normal modes. So what you can do, and this actually is not too hard to do, you can go through and download a seismogram of a large earthquake, and using something like seismic analysis code, which we will do in one of our tutorials, you can do a Fourier transform. And if you look at the lowest frequency, so this is 0.0004 hertz, you will see the different normal modes. That there is multiple normal modes around a particular high point. It suggests there is splitting. So here S30 has some splitting, here S20 has some splitting. And that is because we have multiplets. So if we had a solid non-rotating isotropic Earth, for a given M and L, or for a given N and L, all eigenfrequencies for M are the same. So this is known as degeneracy. However, due to the Coriolis effect, due to the elliptical nature of the Earth, since the Earth is not a perfect sphere, due to 3D variations in velocity and density, there are different frequencies and eigenfunctions for each L and M, but importantly, the different values of M lead to these singlets. So we call the collection of these a multiplet, and the individual peaks the singlet. So if I had a SNREI Earth, an SNREI Earth, all these singlets would collapse into the central wave function. However, due to this non-symmetry in the Earth, we actually have each M value creates a different, slightly different frequency. So just to put it graphically, rotation affects things. So waves in the direction of rotation travel faster. Ellipticity affects our normal modes because waves from a pole to pole run a shorter path than along the equator. And then waves are slowed down or accelerated by velocity heterogeneities in the Earth. So here's an example. So we will recall that M can vary from minus L to plus L. So L is 2 here, and the multiplets are M equals -2, -1, 0, 1, and 2. And here we see the different multiplets. All right, and I'd like to thank Michael Van Camp for sharing some of the surface wave figures that I used. All right, does anyone have any questions on normal modes?
Good morning, sir.
Hello.
I have a doubt actually.
Yes.
Up to what depth we can map using normal modes? structural way at the structure.
What kind of structure?
Up to what depth inside Earth we can map using normal modes? Is it like surface waves only or any other application is there?
Well,
Did you get my question, sir?
I think I understand it. So, for instance, we have the preliminary reference Earth model or PREM model, which gives the density, S wave velocity, and P wave velocity in a radially averaged Earth. And that is partially derived from normal modes. I wouldn't use it for local seismology, but I would use it for global seismology. Did that answer your question?
No, sir. Actually, up to what depth means suppose Moho or shallow depths we can map using normal mode. Is it possible to modes to map Moho or only it is applicable to shallow depths to understand shallow nature of the Earth?
No, I wouldn't use the normal modes to map out the MOHO depth.
Okay. Is there any reference paper you can suggest?
On normal modes? Yeah,
Normal modes.
I'll look for something and I'll post it.
Okay, thank you, sir.
Yeah.
So I have another question.
Yes.
So earthquakes are mainly shear events, right? Slipping on a fault. Okay. So I was just a bit confused. Like, what does normal mode have to do with an event that's mainly shearing on a fault? You know, maybe I'm wrong, but how are those two related?
Well, any earthquake will excite normal modes. I couldn't tell you exactly what A values, so A is the amplitude of the excitation function, that a particular focal mechanism of an earthquake would generate. But I can't say a strike slip fault or a reverse fault or a normal fault will all generate normal modes.
Thank you.
Yep. Okay, let's take a 10-minute break and then we will start refraction seismology. All right, I think it's been 10 minutes. So I will now start refraction seismology. This will be a shorter lecture, and then we will go on and do, I'd like you to start homework 2 and homework 3 if you haven't already. All right, refraction seismology. So if you are reading the PDF I posted from the Stein and my session book, this is chapter 3.1 to 3.2. So we've basically developed the basis of seismic wave propagation theory. And now we're going to talk about usefulness of seismic waves for inferring Earth structure. I'd like to begin by talking briefly about inverse theory. So in forward modeling, if I have a cannon and it's at location X naught, it shoots a projectile with a velocity V naught at an angle theta naught, a forward model would say, given X naught, V naught, or theta naught, what is X, where X is the location where the projectile lands. So we have some function of source, a model of perhaps the air that the projectile moves through, and that gives us data, which is X. In inverse theory, we say, given X, what can we infer about X naught, V naught, or theta naught? So we take the data and we try to infer information about the source or the model. And you can imagine if I know the projectile landed at X, well, I could have a one X naught and one V naught that fits the data, as well as another X naught and another V naught that fit the data. So inverse theory will often create a multitude of possible solutions. So a seismic example, we can say the travel time of a ray that goes from a source to a receiver is the integral from the source to the receiver of 1 over the velocity structure it travels through times dx. So forward modeling would be taking the source and receiver locations combined with v of x to calculate the travel time. Inverse modeling would be taking the observed travel time and inferring the velocity structure traveled through. And there are many ways to do this, and expertise in inverse theory is one of the hallmarks of a good seismologist. And to be honest, we won't actually get to any more inverse theory other than that. But let's look at some ways to get a velocity structure using refraction seismology. So refraction seismology typically involves using waves that are critically refracted at interfaces to infer Earth structure. So here's a simple example. We have a layer of thickness H naught and velocity V naught over a half space with velocity V1, and V1 is greater than V naught. It produces a direct wave, a reflected wave off the interface, and a head wave that is refracted at the interface. So you might recall the head wave was the evanescent wave that I talked about in the previous lecture. Types of sources can be a sledgehammer, a shotgun, a vibro-sized truck, an explosion, a nuclear bomb, or an earthquake. And all of these have been used for refraction seismology. So in particular, we're going to focus on this blue line here. So, but I do want to show you the three types of waves. So the direct wave, the time of the direct wave is just the distance between the source and receiver over the velocity of the top layer. So on a plot of x versus t, the rivals of the direct wave will have a slope of 1 over v naught. The reflected wave, just using the Pythagorean theorem, is going to have a travel time of 2 times the square root of x squared over 4 plus h naught squared over v naught. And I can simplify that in terms of this here. This will form a hyperbola on a travel time distance plot. And finally, we will have a head wave, and the head wave will have this velocity here. We will note that only one component varies with distance, and that's going to have a 1 over v1, or 1 over velocity of the layer 1 dependence. So if we can calculate the slope of the travel time versus distance, we can get the velocity of layer 1. This here just defines the travel time in the crust. This defines the travel time that it's propagating along the interface. And it's actually propagating just below the interface, which is why it sees velocity v1. So if I have a source at x equals 0 and a bunch of seismometers that are spread out over increasing distance, in my simple interface, I will see the direct wave as this dashed line here, and that will have slope 1 over v naught. I will see the head wave, and that will have a slope 1 over v1, and I will also have the reflected wave. Now, typically in real seismograms, it's easiest to see the first arrival. So the first arrival will be the direct wave until I reach the crossover distance, at which point it will be the head wave. So we would calculate 1 over v naught from this wave and 1 over v1 from this part of the travel time distance diagram. The critical distance, that's the distance at which the head wave first appears. That's 2h naught times tangent of the critical angle. So that's basically, I go from the source, hit at the critical angle, and then go back up at the critical angle. And the crossover distance is 2h naught times the square root of v1 plus v naught over v1 minus v naught. So it's going to be a function of the direct wave slope as well as the head wave slope. So here's an example. This is a record section. And a record section is seismograms plotted by location of seismometer from the source. I should say seismometer, but it's not quite spelled properly. The move out is a change in phase location as a function of distance. So for instance, here's the direct arrival, P sub G, and we can see that the travel time varies as a function of distance. So that's called the move out. The reduced velocity is this time axis is changed, so our horizontal line would correspond to a specific velocity, in this case, 6 kilometers per second. So phases with a move out that has a negative slope has a velocity that's less than 6 kilometers per second. And a phase with a move out having a positive slope are seeing a velocity greater than 6 kilometers per second. And this is typical of a PN wave. A PN wave is a head wave that travels at the base of the moho. And typical PN velocities are between 7.8 and 8.2, 8.4 kilometers per second. We also have a PMP, which is a bounce of the size of the wave off the moho. So that's the reflected wave. So this reduced travel time plot provides an easy way to distinguish velocities and actually identify the PN wave, because a PN wave would not occur with a velocity less than 6 kilometers per second. And if we plot the move out of our direct and head waves, we can get velocity 0 and velocity 1, because the direct wave is x over v naught. So the slope is going to give us 1 over v naught, and the slope of the head wave is going to give us 1 over v1. Now, the principle of reciprocity is that if you switch the source and receiver, you would see the same travel times. So here's the source and here's the receiver, and here's the source and here's the receiver. You would have the same travel time. This is called reversing the line. And this is, you put the receiver on one side and the other side of the source. And this is a good way to determine if your interface that you're traveling along has a dip. Now, if I have 2 layers, then I have the direct wave, the first head wave, and the second head wave. And it has this sort of geometry here. So if V2 is greater than V1, and that's greater than V naught, and the layers are thick enough, the head waves for each layer will be first arrivals at some offset. Now, there are exceptions to this, and that's the low velocity layer or a thin layer. So if V1 or if V2 is less than V1, we won't have a head wave here because there will not be a critical angle. The actual ray will refract downward rather than upward. Also, if the layer is thin enough, what can happen is the velocity of the second head wave can come in quicker than the velocity of the first head wave. So here, this dashed line shows the slope 1 over V1. So this is the arrival time of the first head wave, and this is the arrival time of the second head wave. And if the velocity of the second layer is fast enough, and the layer of layer 1 is thin enough, this second head wave will arrive before the first head wave. And typically, this stuff that is not the first arrival will be obscured by noise. So a way that you would determine this is perhaps through other means, like a well log, outcrop data, a geologic map, for instance. So when we're talking about sort of nearer surface structure, it's quite useful to use other geological information to try and get some constraints on your seismic results. If we have dipping slanting layers, I have a source here and receivers going out to the right, and then I have a source here and receivers going out to the left. We will have different slopes, and those slopes will be a function of the up dip and down dip slope. And you can actually calculate the relative dip from this. We won't go into that here. And in refraction seismology and reflection seismology, in terms of its near source use, there's a lot of details that this could actually be a whole class. And we're just going to do it as 2 lectures. So here's an example from the deep probe experiment, which set off a massive explosion with the goal of imaging the North American lithosphere. And they saw a PN wave, a PN2 wave, which is a second interface that they found between the crust and mantle. They found a PIP, which is a reflection off an interface, and a PMP, which is a reflection off the MOHO. Now, these are great for getting detailed seismic velocity plots of the lithosphere or the crust. It can examine small scale structure in much more detail than earthquake-based structure. But it's expensive and it's difficult to permit large explosions. So there are disadvantages as well. Typically, we will also use refractions that are not just head waves when we do academic seismology, and try to use a simple layer approximation to use as a starting model to invert for more accurate velocity variations. So using this top plot here, this is travel time minus the distance divided by 6 seconds. So again, this is a 6 kilometer per second will go up, and a greater than 6 kilometer per second move out will go down. And we see this sort of structure based on these arrival times. So with that in mind, we can get crustal thickness and P and velocity for the United States. This is actually old stuff from when the book was written, which I think was in the late 80s or early 90s. And you get much more accurate representations of P and velocity, which is this bottom plot or crustal thickness from passive source seismology. Another thing to note is what velocity variations really mean. In the crust, velocity variations are primarily due to composition. So basically, as I go from more felsic to more mafic rocks, the velocity goes up. Sediments are slow, igneous rocks are faster. More mafic velocities, more mafic rocks have higher velocity, but it's actually a lot more complicated than this simple plot would show you. All right, that is refraction seismology. And what I'd like to do now is spend time with you guys going over the homework. So I'd like you to start homework 2 and homework 3 if you haven't already, and ask me any questions. And I will be back in 10 minutes. So I will be back. Yeah, I'm not sure what time it is there, but I'll be back in 10 minutes. All right, everyone. So I would like to answer any questions on the homework. So I will just be here waiting for the next like 25 minutes, ready to answer any questions that you have. This homework 3 and I think homework 1 are probably the longest homeworks and probably the most challenging. And the homeworks after that, these two are much simpler and shorter. Any homework questions yet? No? Okay. Is it useful that I'm giving you all some time to work on the homework?
Yes, sir.
It is, okay. All right, good. Otherwise, I just fill this with lecture, but I thought it would be good to spend some time catching up on the homework.
So you provided the solutions as well, so that's also great. We can consult when needed.
Okay, good. Well, I will give a few minutes at the start of my next lecture on to discuss any homework questions as well then.
Okay, sir, thank you.
Mhm.
So in homework 2, first question, I'm getting confused in beta S and beta 1. Hello.
Oh, sorry. I thought my microphone was on, but it wasn't. So you were
Hello?
confused at the first question?
Yes, sir. All thing is okay, but beta S and beta 1. So beta 1 is the shear wave velocity in the first layer. And what about beta S? So is it average velocity at the boundary between the two layers?
So beta 1 is square root of mu over rho in the top layer.
Yes. Yes, sir. That
Beta 2 is square root of mu over rho in the bottom layer.
Yes.
Oh, and the formula has beta S, which
Yes.
is just wrong. That should be beta 2. Oh no. Yeah, I think it's beta 2 in the formula that I give.
Thank you, sir.
Mhm.
Sir, hello.
Yes.
Sir, do we have to send both tutorial homework and class homework to your mail, or only tutorial homework?
I'm sorry.
Like
Did-
tutorial homework is related to Linux programming and all.
Yeah.
This class homeworks are there. So do we have to send both to your mail?
You can send either or none. It's up to you. If you would
Okay.
like me to look at it, I'd be
Yes.
happy to.
Okay.
But if you're happy just looking at the answer key, that's fine too.
Okay, sir.
Mhm.
Thank you. Sir. Thank you.
Yep. All right, it's about time to finish up this morning's class. So Mohit, do you have anything to say?
No, that is all. Thank you.
All right. I will see you all tomorrow night or tonight. Sorry.
Yeah, tonight.
Okay. Bye, everyone.
That's it. Thank you.
Thank you, sir.
Bye, sir.